today I want to talk a little bit about generating functions. So generating functions are not going to be functions in the strictest sense always, or at least we're not going to worry too much about the domains of these functions or what their values are, but they're more just a way for us to take some information and organize it. So for generating function, to deal with generating functions, you might want to review Taylor series from calculus. You just might want to look over some of that stuff. In general, we will communicate the sequence aj as j goes from 0 up to infinity by writing a function f of x, which is an infinite series. That is the series as j goes from 0 to infinity of aj times x to the j. So this is just another way of keeping track of these aj's. Now, it might not be obvious why this is a good idea, but that's what hopefully we'll figure out in this section. So let's start by considering the sequence. Aj is 1 for all j's. Right, so this is just the constantly 1 sequence. Well, as a sum, if I'm writing it out like this, then the corresponding, what I'm going to call a generating function, is going to be 1 times x to the 0 plus 1 times x to the first plus 1 times x squared plus etc. And that gives me this infinite series. The sum as j goes from 0 to infinity of just x to the j. And so now we might want to say, well, fine, but what's the point? What have we gained? Well, if we remember a little bit about infinite series, we may have seen a derivation like this sometime in the past, which is, let's take x times f of x, which will be exactly this, but multiplied by x. So I'm going to have x plus x squared plus x cubed plus dot dot dot. And this is just the sum as j goes from 1 to infinity of x to the j. So I'm just writing this as a formal power series. I'm not concerned about where it converges or what it equals. And now if I subtract these two, then I have f of x minus x times f of x equals, well, notice everything is going to cancel out here. X minus x squared minus x squared, x cubed. Everything's going to cancel out except for the first term. When I subtract these two sums, I'm going to be subtracting everything except for 1. So this is going to be 1. And just to, point this out, this is going to be the sum as j goes from 0 to infinity of x to the j minus the sum as j goes from 1 to infinity of x to the j, which is just going to be, x to the 0. It's the only thing that's left. So I have this nice relation, which is f of x minus x f of x is equal to 1. Well, if I do just a little bit of algebra on this, I can see that 1 minus x times f of x is equal to 1. And this tells me, finally, that f of x is equal to 1 over 1 minus x. Now, you might say, well, I knew that when I looked at this. I knew that by maybe knowing how a geometric series works or something like that. And that's fine. But this is just another derivation. So I can communicate the all ones sequence, namely the sequence where every element is a 1, by writing down this particular function. At this point, you might still be saying, okay, what's the big deal? No worries. Let's do another example. So let's now write the sequence, consider the alternating sequence, let's do 1, 0, 1, 0, etc. And so what I want is, I want to find some function. In this case, my f of x is going to be, some sequence, these aj's coming from this set, x to the j, and I want it to be 1 plus x squared plus x to the fourth plus dot dot dot. So how do I do this? Well, again, what I can do is run the same trick, except with, instead of x, with x squared. And so I want x squared times f of x to then be, whatever this formal sum is, to be x squared plus x to the fourth plus dot dot dot. And now I can do the same trick that I did before and write f of x minus x squared f of x, and I'll get 1, which gives me, by a similar manipulation, that f of x is 1 over 1 minus x squared. And you might say again, well, Steve, this isn't that complicated. This is, again, just a geometric series. Okay, all right, that's fine. That's fine. Let's try something now just a little bit different. Let's say we want the same sequence as before, but starting at 0. So I want the exact same function as before, but sort of shifted over by 1. Well, that's nice. If I have from before that 1 over 1 minus x squared is going to give me 1 plus x squared plus x to the fourth plus dot dot dot, then I can multiply both sides by x, and I'll get x over 1 minus x squared is x plus x cubed plus x to the fifth plus dot dot dot. So this 0 is the coefficient of x to the 0, so I get 0, 1, 0, 1, 0, 1. And hopefully, at this point, we're not scared of this. I mean, this is an infinite series, but again, I'm not trying to evaluate it. I don't care what f of x is or anything for a specific x. X is just a symbol. I want you to think of x like a comma, okay? X is just keeping track of things for us. So that's one type of manipulation. Let's move on to a different type of manipulation. So if I forget a little bit about mathematical rigor and calculus, let's take this equation that we've just sorted out. 1 over 1 minus x is equal to 1 plus x squared plus dot dot dot. So this was the first generating function we came up with. Let's take this and differentiate both sides. So if I differentiate both sides, I'm going to have d dx 1 over 1 minus x equals d dx 1 plus x squared plus dot dot dot. And what I want to do is, again, ignore convergence or whether this is well defined or anything like that. Just treat x as, like I said, like a comma or a delimiter. And then for a second, I want to pretend that I can do calculus on this little comma or delimiter. So I'm kind of having it both ways here. Don't worry too much about how rigorous this is. Just walk with me. Now, if I take the derivative of this left-hand side, I can do the quotient rule and get, low d high minus high d low. So, the way that I do the quotient rule, just because I'm slow, and haven't come up with something better, is low d high minus high d low over the square of what's below. This is still the little song I sing to myself. So if that reveals something about my mathematical immaturity, I'm sorry. So low d high, so I'm going to have 1 minus x times the derivative of 0 on top here. And that's, sorry, the derivative of 1, which is 0. So I have 0 minus high d low. So minus 1 times the derivative of the bottom, well, that's negative 1, over the square of what's below, 1 minus x, quantity squared. And now let's take the derivative of each of these term by term. And what do I get? Well, I get 0 plus 1 plus 2x plus, and if we had x cubed here, then this would be 3x squared plus dot dot dot. And now let's simplify these. Well, this becomes a minus and negative 1 becomes just 1 over 1 minus x quantity squared. Notice that's a different expression from the expression we had in our second example, which is 1 over 1 minus x squared. So this was just x squared in the previous, or two examples ago, where this is the entire quantity squared. And on the right-hand side, now we've got this sequence, which I'm going to write as the sum as j goes from 0 to infinity of what? Well, 0 is just 0. The coefficient of x to the 0 is 1. The coefficient of x to the 1 is 2. The coefficient of x to the 2 is 3, etc., etc. So we see that we've got j plus 1 times x to the j. Now this is generating the sequence 1, 2, 3, 4, 5, etc. Well, I guess, yeah. So starting at 0, it's generating the sequence 1, 2, 3, 4, 5, etc. because the sequence is j plus 1. Again, if I wanted to multiply or divide by x, I could shift that around in various ways. But hopefully you see this is a slightly different sequence. So let me just write that down. This is aj, j goes from 0 to infinity equals 1, 2, 3, dot, dot, dot. Okay, so now the previous examples were constantly 1s or alternating 1s and 0s, alternating 0s and 1s. Now we've got, 1, 2, 3. So I'm hoping that at least you're convinced that there's some power here. Maybe we're not doing anything ultra complicated yet, but this is another way to generate and communicate sequences. So before I finish, I want to just give you one little statement. So proposition 1. So let's let a of x be the sum as j goes from 0 to infinity of little aj x to the j, and we're going to let b of x be the sum as j goes from 0 to infinity of little bj x to the j. Then we have that the product a of x times b of x, so just the function which is a product here, so this isn't like a convolution or anything like that. Well, you'll see how it relates to convolution if you've heard of that before. But this is, I'm just multiplying two things together, is going to be the sum as j goes from 0 to infinity of cj x to the j, where each cj is the sum as, let's say, k goes from 0 up to j, a sub k, b sub k minus j. So what we have here is, wait a minute, this will be 0, this will be 0 minus 0, no, this should be j minus k, sorry about that, gotta fix that in my notes. So, yeah, so for a fixed j, we're going to be going through and taking all of the pieces where ak, where subindices ak and b, j minus k are going to add up to j. So just let's do a simple example of this. Let's look at the first few. So let's look at the first few, and this is just higher level foiling, if you want to think of it that way. But let's just see, for example, consider let's look at the fourth term of a of x times b of x, where we've got some sequence of aj's and bj's. Well, that's going to be the fourth term. So c sub 4, or it's the fourth coefficient. I guess that'd be the fifth coefficient. But let's look at the j equals 4 term, which is the fifth. Yeah, you know what I mean. C sub 4 is going to be the sum as k goes from 0 up to 4 of a sub k, b sub j minus k. So this is going to be, well, so when k is 0, I've got a0, b, and j here is 4. a0, b4, plus a1, b3, plus a2, b2, plus a3, b1, plus a4, b0. And if we were to take two just polynomials, if they weren't infinite series, but two polynomials together, both of degree 4 or greater, then the coefficient of x to the 4 would have this form. So hopefully that made sense. Sorry about, I had those indices backwards earlier. Sorry about that. But hopefully this makes some sense. And now we are ready to start talking about what we can do with generating functions in the next lecture. Thank you.